We're looking at a chandelier suspended above the street at the Americana Shopping Center in Glendale, California. And this is some architect's design idea to put a chandelier out there in the middle of the street. And it's a problem in static equilibrium. We want this chandelier to stay static. We don't want it moving. And so they've got a pair of cables being pinched by the chandelier cable here. And it's connected to a building on the left and a building on the right. Looks like the cable is horizontal on the left and there's an angle to it on the right. As I say, this is a problem in static equilibrium. And I've drawn my representation of the chandelier, and I've simplified the cable such that it's just a vector pointing left and a vector pointing right and a vector pointing down. And as I say, it's a problem in static equilibrium where we want to know how strong should these cables be. If you've gone fishing, you talk about the test strength of your fishing line, and maybe it's a 40-pound test. Well, 40-pound test probably won't be strong enough to support the chandelier. I'm estimating the chandelier to be 400 pounds. I don't know what it is really, but I'll estimate it. I think that's a fair enough estimation. And I'm going to say that we'll call this vector F1 and we'll call this vector F2. And with our vector trigonometry, we can solve for the magnitude of these vectors and determine the strength required, the test strength. So here's the question formally. Find the test strength of each cable required to suspend the chandelier above the street. That's what we'll look for. We want to find the magnitude of F1 and magnitude of F2 in pounds. I'm going to call this another vector down here. That's F3. F3 is a gravitational force of 400 pounds, so it's a vector in the vertical, well, negative vertical direction anyway. I should also say something else about these vectors. We know if I put in a coordinate axis, in other words, I put in the horizontal x-axis and I put in the vertical y-axis, I'm going to estimate this angle to be 30 degrees to F1. And to F2, F2 is a straight angle, so that's 180 degrees. So we know the direction angles on these vectors. We actually know it on F3. We know both the direction and the magnitude. It's a 400 pounds, so that would be the magnitude would be the 400. We don't know the magnitudes of F1 and F2, as I say. And we want the chandelier to stay static. And what that means is we need vectors F1, F2, and F3. If I indicate these as being vectors with my little arrow here, we want the sum of those. We want the sum of those to be 0. Well, that means the 0 vector. To add those up, as we've seen in our discussion on vector operations, the easy way to add vectors is to get them in component form. If you recall, if I take, for instance, a standard vector V, it has a horizontal and a vertical component. And that's what I'd like to get. And so, in other words, to represent vector V horizontally and vertically in its horizontal and vertical components, we take the magnitude of V times the cosine of the direction angle theta. That would be that theta in there. Direction angle theta times the unit vector I. That means we're in the horizontal direction. If you recall, the unit vector I is that horizontal unit vector times the magnitude of V in the vertical direction times the sine of the angle, and that's in the vertical direction. The unit J vector, remember that's the vertical one. I'm going to color code these. So that's the blue, and the vertical, as we see in the diagram, is the orange. All right, and so we want to get F1, F2, F3 in that component form. And so I'm going to use that formula. I don't know the magnitude of F1, so I'm also putting in a variable, F1 magnitude, times the cosine, and I've got the angle at 30 degrees. If I look over here, I've got it 30 degrees in the horizontal direction. Magnitude of F1 again, following the formula above, times the sine, as the formula says, of the direction angle 30 degrees. That's in the J direction. Similarly, F2 is going to be the same thing. The magnitude of F2 times the cosine. Now I'm writing 180. Do you see why I'm doing that? That's the direction angle to the F2 vector. F2 times the sine from the formula above, 180 degrees. That's the direction angle in the vertical direction, which I represent by that unit J vector. F3 is a little nicer. It has no horizontal component. It's strictly straight down. That means it has 0 horizontal in the I direction, in other words. Negative 400. It's going vertically down, so I write 400 J. All right. All of this is supposed to be 0I plus 0J. That's the, as I say, it's supposed to equal 0, or the 0 vector if we're adding vectors, and that's what we're doing. All right. I'm going to take these equations and rewrite them such that we can have a nice system of equations. So I'm going to highlight something I'm going to do. I'm going to take this first vertical series of components. I'm going to rewrite them this way. I'm going to take it as F1 cosine of 30 degrees added to, the next one down is F2. You'll see why I'm doing this in a minute. Cosine 180 degrees. And then there's 0. I'm not going to put the 0 in there. But the line here does, should extend that. That line equals, it says that down here we're equal to 0. You notice I didn't put I didn't put the I's here. I didn't put I there and I there and I there. I could. There they are. But they divide out. So we don't need them. I'm going to do the same. Let me highlight this. I'm going to take this series of components, the vertical components. I'm also going to write them across similarly. It starts with F1, the sine of 30 degrees, plus F2 times the sine of 180 degrees, minus 400 is what's next as I look down that blue highlight, and that below the line is equal to 0. I'm going to take that minus 400 and move it to the other side. So that means we'll end up with equals 400. Now, the reason we did this is we now have a system of equations and two unknowns. And the unknowns are the magnitude of F1 and the magnitude of F2. That's an unknown there, an unknown there. Two equations in the two unknowns. And we'd like to solve for those unknowns, and we're set up for that. What we'll do now, we can take this top equation and rewrite it. F1 cosine 30 degrees equals, I'm going to move the F2 cosine 180 degrees to the other side. And now I'm going to solve for F1 by dividing out cosine 30 degrees from both sides. And what that gives us is that F1, the magnitude of F1, get these little vector arrows back in there. I get out of the habit of writing those. But okay, F1 is equal to minus F2, and now we need to take cosine 180 and divide it by cosine 30 degrees. If I take the calculator and I take 180, we know the cosine of 180 is minus 1, but here it is in the calculator, and divide it by cosine 30, and that's equal to minus 1.1547. Minus 1.1547. I take it to 4 decimal places. This is to say that F1 is equal to 1.1547 times the magnitude of F2. I should have been saying the magnitude of F1 is equal to the 1.1547 times the magnitude of F2. Well, that's pretty nice. Now I can take this second equation, I'm going to rewrite it, F1 sine 30 degrees plus F2, magnitude of F2, magnitude of F1, times sine 180 degrees is equal to 400. But because I know that F1 is equal to 1.1547 F2, I'm going to replace it. I'm going to take this out, and I'm going to replace it with 1.1547 magnitude of F2. So I have 1.1547 F2 times the sine of 30. Sine of 30 is 0.5. Let's see. So I can rewrite this. Let me write that. 1.1547 times 0.5 is equal to 0.57735. 0.577, I'm going to round it to 4. As I say, I'm taking 4 decimal places. So this first term comes out to 0.5774 times the magnitude of F2 in our calculator. That's what we got. And then sine of 180, oh, that's nice. If you recall, sine of 180 is just 0. I'll verify that here. You see that sine of 180 is 0. So that's plus 0 is equal to 400, which tells us that F2 is equal to 400 divided by 0.5774. That's going to give us that F2 is equal to, let's see what that is in the calculator, 400 divided by 0.5774. That's 692.76. 692.76 what? What were we doing? We were finding the tension in a cable. It's 692.76 pounds. Test strength. The magnitude and the test strength of the cable that we need. It's the magnitude of the vector and the test strength. So we found one of the answers. Now we need to find the next answer. I'm going to take this information and I'm going to plug it in to this formula for F1. It says it's 1.1547 times F2, but F2 is 692.76, and so we'll get F1 is equal to, let's see what we have in the calculator. Calculator, I have it to all my places, and so I'm just going to multiply that by 1.1547, and we'll take it to 2 places. That's the way we do the final answer. Take it to 2 places. 799.93. 799.93 pounds. That's the magnitude of the F1 vector. It's the tension strength, the test strength that that cable on the right would require. And that's our final answer.